All right. Michaela. Well, I'm good. I don't know about you guys. Yeah, Sarah.
Will you go over number 3 on the exam? I know you drew an explanation on the answer key, but can you talk about it?
Yeah, so this one is a little tricky. So if you try the replacement test, which is what you should always do in these situations, what you're gonna find is we have a methyl here. So we can end up with the deuterium on the wedge versus the other part of the replacement test where we put the deuterium on a dash. And so the tricky part about this one is that methyl, is it a chiral center in this molecule?
Yes.
Well, not in this molecule, right? Because we've got the symmetrical ring. We've got CHs going all the way around. But when you try the replacement test, now we end up with a deuterium here, and so this becomes a chiral center. And so one chiral center, you can look between these two molecules. The methyl keeps the same stereochemistry where the deuterium changes stereochemistry. And so are those enantiomers or diastereomers? Yeah, those are diastereomers. So that means we have diastereotopic protons. And so how many signals do you see for diastereotopic protons? 2.
So, well, why is that? Why?
So basically, we're just following the replacement test, right? So you might have picked up on the fact that have I ever shown you any just plain cyclohexane rings in class or in lab or in terms of NMR? There's been benzene rings and there's been some special cyclic systems, but there's never been any cyclohexanes. And so the reason is, if you look up the NMR spectrum for a molecule like this, what you end up having is each of those CH2 groups are diastereotopic because, and we can show it right here with the replacement test. So if we try the replacement test, you can see that these are diastereomers. If we do the same thing with the CH2s here, maybe not there, but at least here, here, and here, those are all going to be diastereotopic protons. So what you end up for a cyclohexane, or at least with a lot of cyclohexanes, is a bazillion different signals that smudge together. And that's why I never give you any cyclohexanes for an NMR problem, because you never get a really clean spectrum. You're just full of diastereotopic protons. So basically, you try the replacement test, you see you've got diastereomers. So,
Well, why does that make them give different signals?
because they're in different chemical environments, right? So obviously the proton on the wedge here is on the same side as the methyl. The proton on the dash is on the opposite side of the methyl. And so they're in different chemical environments, and so we see we see different signals. And that's not as obvious until you try the replacement test. Questions about that? Yeah.
Would that ring then have 7 different signals?
That ring, how many signals would that ring have? That ring would ultimately have a total of 1 here, 2, 4, I think that in fact would be, so 6, 8, 10. I think you'd see 11 signals total for that cyclohexane
For
ring.
the symmetry,
Yeah.
if
What do you think about?
you have symmetry, since the carbon next to the methyl is consistent, that would be the same on both sides with that.
Are you talking about this position? So if we look at that, we should see something similar. So we should have methyl deuterium versus deuterium hydrogen. And so again, we're going to have a pair of diastereomers, right?
Yeah.
And so there would be 2 signals from that CH2. And in fact, I'm also forgetting about the hydrogen that's off of that carbon right there, that tertiary carbon. So you'd end up with 1, 2, 4, 6, 8, 10, 12 signals. And so that's again why you never are given that sort of problem.
Wait, I think she meant that the one on the left and the one on the right of the.
Oh, you're talking about these two.
Yeah, and yeah.
Oh, I understand. Yeah, no, that's a good point too. I didn't consider that.
Will those be the same signal or is it just-
Let's think about that for a second. Those might be equivalent, but then you've got the added. In reality, I think that you'd find that this spectrum is really smudgy because you don't have free interconversion between the chairs, right? So one of these chairs is going to be more favored than the other chair, the one with the methyl and the equatorial, but you're going to see signals for both. So that's another complicating factor. So that's why you never see a cyclohexane spectrum or something in class. They're complex. I thought this one would be a little more straightforward. Not a lot. Rhea?
Number 2.
Were there any questions about that? Okay, so number 2, an alkenyl proton is further downfilled than an alkynyl proton on a proton NMR spectrum because. Okay, so A and B, which is a true statement? It's B, right? So B has more S character, and so because it has more S character, sp orbitals are more electronegative. So A is definitely not right. So then if we think about that, let's think about what we see. So we typically see sp3 CH bonds around 1.0 ppm, and then we see sp2 CH bonds around, protons around 5 to 6 ppm. Where do we see alkyne protons? It's around 3. And so even though alkyne protons are that we do have more electronegativity from those carbons, what we find is that, well, that's not what, we don't see these further downfield, right? They're actually further upfield around 3. And so what I was getting at is the fact that, well, since we, I read sp3, sorry. Those are sp, right? So here's our alkynes, and here's our alkenes. And so the statement says an alkenyl proton is further downfield than an alkynyl proton. So that's true, we see that's true, but it wouldn't make sense for it to be because of electronegativities, right? Because if it was because of electronegativities, we would expect the sp-CH protons to be further downfield. But that's not what we see. We see they're actually around 3. And so what it ultimately is just the anisotropic effect that causes the different shift. So I still gave some partial for D and E because you've got the anisotropic effect, but ultimately A and B don't really play a role in it. So it's just C.
So it is more electronegative, the sp hybrid orbital because of the lower S character.
Yeah.
But it doesn't make sense for like the question.
Right, so if there was no anisotropic effect, you would expect the alkyne proton to be further downfield. But the fact is, that's not what we see experimentally, and so it must be the anisotropic effect that causes a shift back.
Thank you.
Yeah. Other questions about that? All right, Michaela?
Can you do number 4?
How many signals appear in the proton? Okay, so let's see. Let's just draw them all out. So what we've got is this molecule, and so we've got a CH3 here. And then we've got an alkyne here. So we've got proton, 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 and these. Okay, so clearly our methyl, and I'll just number them. So we'll say A. How many different benzene protons do we have? Yeah, those should all be an equivalent, so we'll just say B, C, D, E. Clearly this is going to be its own thing, and I think this is what tripped a lot of people up on this question. So when we look at the external proton, or I'm sorry, the terminal protons here on the alkene, are those the same or are they different?
They're different.
Those are definitely different, right? And so the reason for that is this proton right here is always going to be trans to the benzene ring, right? And so this proton here is always going to be cis to the benzene ring. We can rotate this bond, but that's not going to change that relationship at all. So we're still going to have these two in different chemical environments. One will always be cis, one will always be trans. Yeah.
Yeah, for the last NMR problem that they also have us alkene on, but on the spectrum it only shows up as 1H and 2H.
We'll take a look at that one. Let me, all right, so this is going to be 1, 2, 3, 4, 5, 6, 7, 8 different ones, so that's D. A lot of people put 7, and I think the issue was getting G and H confused as being equivalent. On that last spec problem that you're talking about, so if we can zoom in, I don't know how well I can zoom in here. Really what you're seeing here, so you've got a clear doublet of doublets right here, right? So that's a clear doublet of doublets, and then it says that we've got 2 protons here. Now this was on one of the practice exams, this came up. So when we look at the signal right here, is that a doublet of doublets, or is that basically 2 doublets? It's 2 doublets, and you can recognize that by look at the gap. So you see over here, let's call these peaks A, B, C, and D. All right, so the gap between A and B, and then the gap between C and D, is that the same or different? Yeah, it's the same, right? It's the same distance, the splitting that's going on there. And so that tells us that that's the same proton that's being split by the same amount. When we look over here, let's call this A, B, C, and D. Is the gap between A and B the same as the gap between C and D? No, it's not. And so what's going on is these are still, basically we have a line running down the middle here, where the ones on the left, the 2 peaks on the left are one of the alkene protons, and the peaks on the right. And ultimately, these are both doublets of doublets, except one of the splittings, one of those J couplings or J values is really, really small. And so if you look at this really closely, you might be able to tell that this signal right here is actually split into this tiny, tiny little doublet. But that's what's going on there. So ultimately, we see that these two are inequivalent, and so what that tells us is that makes perfect sense for us to have a pattern like that. And ultimately, it also makes sense. And so let's think about why that would be. So which, all right, this is a good question. Which of these protons do you think is this one? We'll say, we'll call them.
Which one?
Yeah, so we'll call them A, B, and C. And so which of these protons do you think is this signal right here? Yeah, I like C, and let's think about that why. So remember our coupling sizes, our big couplings are trans, and then our middle couplings are cis, and then our small couplings are what we call geminal. So what does geminal stand for? That's when they're on the same carbon, right? It's like twins. And so what's going on here is that this is very much going to be C, because you can see that there's basically 2 big splittings going on. That's why we see a clear doublet of doublet. And that makes sense because it's going to be cis to this proton and trans to this proton. So the splittings going on here are going to be a big one and then a middle one. Over here, both of these are going to have a geminal coupling, right, which is really, really small. So this proton is going to have a trans coupling and a geminal coupling. So it's probably that one, because you can see it's split big, and then it's split just very tiny so that you can barely see it. So probably this signal right there is going to be A. And then that leaves this for proton B, and that makes sense. So again, there's a geminal coupling. It's very tiny. You can barely even see it. But then there's that middle-sized cis coupling. And so you can see that cis coupling comes from the relationship between B and C. So ultimately, these are actually 2 different inequivalent protons that we're seeing there.
Yeah, I understand that there is different couplings, but
Yeah.
like it shows up as one signal, I guess.
It's not, and so I've drawn this red line down the middle. We've actually got 2 signals. They're just they happen to be, through circumstance, very close in
So
PPM.
the 2H shouldn't be there. Should be like 1H on one side and 1H on the other.
Yeah. Yeah,
So
so
yeah, I
it's-
use that to deduce the first question is whether I have one signal or not. So I thought 2H means that they're together. That means they have the same.
Sure.
environment. So
No, yeah, and I can see a case being made for having given you that information, but I can also see a case being made for expecting you to realize that, especially given some of the practice problems we saw on the practice exam, basically required you to know that part. So, yeah.
while we're here, can we go over this ancient mark?
We can. Okay. So, let's see, what's the IHD?
1.
Yeah, so you should be able to figure that out at this point. So the IHD is equal to 1 here. And so we've already shown that we've got this terminal alkene, and so that basically takes care of that. All right, so we've got that fragment. I think the next big piece of info that you can tell from this is we've got this signal right here. You see that, Matt? Yeah. So we've got this signal right here that corresponds to 6 protons, and it's a singlet. And so what makes sense for that?
2 CH3s.
2 CH3s, and furthermore, how many neighbors?
None.
None, right? Because they're singlets. So most likely, this peak right here is going to correspond to something that looks like this, where that carbon that they're connected to is not connected to any hydrogen. So we've got that piece. And then finally, let's see, we've got a signal right here. And so there's really only one reason we'd ever see something downfilled around 3.5 in this molecule. What is it?
Yeah.
Is the chlorine, right? That's our only real electronegative atom there. So most likely, we'd say that we have a CH2. And so, let's see, let's call this A, B, C, and D. All right, so most likely, all right, this is A. And the A signal is split into a triplet. How many neighbors does it have?
4.
Close.
2.
2. All right, so, and then so what signal must that be?
Well, we don't.
Do-
Could it have another neighbor on the other side?
So there's only one of these peaks that integrates to 2, right? And so the only thing this could possibly be is B, because we only have one signal integrated to 2. And that actually gives us a little more information. So if that's peak B and it's split into a quartet, how many neighbors must it have? 3 total. Now we're already showing 2, so we're going to have to show one neighbor on the right side. So we'll make that a CH. And so what signal must that CH be? Again, that's got to be C, because that's the only signal that integrates to 1, right? So we're basically just kind of snaking our way around away from the chlorine here. So then C is split into a sextet. So how many neighbors must it have? 5. So we're showing 2, and so what are the other 3 going to come from? Yeah, those are going to come from a methyl. And so, sure enough, we also have a methyl that's split into a doublet, and so that makes perfect sense. So we've got our relationships here, and so that's going to be connected somewhere. So now we've got 3 pieces. We've got our terminal alkene, we've got this fragment here, and then we've got this fragment here. So there's only one way to put these together. So what we end up showing would be our terminal alkene with our protons here. This here, CH, CH3, CH2, CH2 chlorine. This one seemed to give people some fits. What do you think the biggest reason was that this gave people fits?
I think discerning the doublet of doublets, just like everything to the left.
Yeah, I thought it would be a little more straightforward just because there was only one IHD, and so then there were 3 alkene protons there. So I was hoping that people would just kind of pick up that there's only one way you can have an alkene with 3 alkene protons.
I know for me, I assumed that the 2s, like the methyl singlet,
Yeah.
the 2 methyls had to, I was like, oh, it doesn't have neighbors, so it has to go on the double bond. But then I didn't have room for the other hydrogen.
Right. Yeah. Ended up being tricky. But I showed it to Abel, and then he said not to feel bad because on his exam he had like a substituted cyclopropane ring or propene ring like that. So I mean, I could have been a lot more evil than I was, I think. So yeah. Yeah.
Could you do number 7?
Yeah. so predict the, I'm gonna sneeze. I'll sneeze in a minute. Okay. So predict a major product for the addition of HBr. And so we know that the addition of HBr is typically an anti-Markovnikov addition. But what is it that determines where the bromine will go? It's the stability of what? Yeah, it's the stability of the intermediate radical, right? So we've got ultimately two possibilities. We're going to have the possibility to have this radical versus this radical. And so which is the more stable radical?
The one closer to the top one, closer to the ring.
Yep, and so this is definitely going to be our most stable radical because there's resonance involved around the benzene ring. And so here's our most stable radical. So we end up with B being the major.
So when we say anti-Markovnikov, using like radicals, it's not so cut and dry. It's like looking at the product.
Yeah, definitely. And I know we definitely said this when we were doing the electrophilic additions, right? We would always say, I would show you something that looked like this. Let's see. So let's say you saw something that looked like this. Now, if you added HBr to this alkane, to this alkene, are we going to end up with the bromine on the tertiary or the primary? Good review for the exam.
Yeah.
All right, so what kind of mechanism is this? It's an electrophilic addition, right? All right, so let's.
Wait, can we go back and explain why does that bromine attach to, why does that being the least stable radical mean the bromine attaches there?
It's the most stable radical.
Right, yeah, so why does that make the bromine attach there?
Because it's the rate, forming a radical here is the rate denervating step for the reaction. And so the radical that is most stable is going to determine the pathway which is favored.
Right, because the bromine attaches and then you have your radical and then
Right, so basically, let's see if I can remember the mechanism for this one. So what you've got is you're going to have, let's see, so we have peroxides, and then our peroxides split into making a bromine radical. So what you've got is a reaction like this. And so we've got regioselectivity here. We can add that bromine to either of the carbons, right? Now the carbon that it adds to is going to be the carbon that leads to the most stable radical. And so by adding in this fashion, such that our bromine, we end up with the more stable. We could consider, I mean, this is possible, it's just not the favored pathway here on the bottom because it's a less stable radical.
So the most stable radical is the least substituted.
The most stable radical, it's the same rule for carbocations, and honestly, this is something that different textbooks will tell you different things, but I think I always think it's best to roll with the easiest explanation. And so substitution makes a carbocation and a radical more stable, unless there's resonance. And so resonance is always going to be more stable. Anytime we can spread it out, that's always going to be more stable than any of the substitution things.
So can you take the double bond out of the benzene ring? Or where would that resonance come?
So what it is you can draw a resonance structure. That looks like that. And so that radical is able to resonate around the entire ring, which makes it a really stable radical. And in fact, that's why I actually gave some points for this answer. It's pretty unlikely that you would ever form this product for a number of reasons. The biggest being that you've broken the aromaticity of the benzene ring. But, you can make a case that it could form. So I gave some partial for that one as well.
Can you just say what happens after the bromine is attached? How does the radical, you just add a hydrogen?
You do a radical reaction with HBr, which regenerates the bromine radical.
Okay.
Yeah. So just a reminder, this reaction up here is an electrophilic. You need to know this for the exam. So it's an electrophilic addition reaction, and so of course, where are we going to add the hydrogen? Are we going to add the primary to the tertiary? Yeah, well, we're going to add it to the one that forms the most stable carbocation, right? And so in this case, by adding it to the tertiary, we end up with this resonance stabilized carbocation right here. And so that's basically the same thing that's going on. So we end up with this sort of regiochemistry and this carbocation mechanism for the same reason that we end up with the regiochemistry we see down here. So by forming our carbocation here, that's the more stable carbocation. If we were to put it here, it wouldn't be resonance stabilized. So this ends up leading to our major product. It's the same thing down here. This is just a more stable intermediate, and so that leads us to our major product. Yeah.
Can you do number 5?
All right, so number 5, what is the... All right, so what is the most stable, I'm sorry, the least stable CH bond in this case? Which one? Not the allylic, the benzylic, right? Because that's the one where we can draw the most resonance structures for the remaining radicals. So we have our least, or our weakest CH bond there. Next would be our allylic. And so after this, we don't have any more that we can abstract to give resonance. So what would be our third weakest? Yeah, it's going to be the tertiary right here. So it would be 1, 2, 3.
Wait, can you explain again why that's?
So you always want to think about what would lead to the most stable radical. And so by forming a radical at this position, we'll have a benzylic resonance stabilized radical. If we do it at the allylic, then we have an allylic stabilized radical. And so this one is the weakest because there's a lot of different resonance structures you can draw on the benzene ring. There's only one that you can draw with the allylic system here. And then finally, this is going to be the third weakest because it leads to a tertiary radical, which is going to be more stable than any potential primary or secondary radicals. Yeah.
I guess I'm kind of confused as to why you can do a lot of different forms with the benzylic one, like how you have a lot of them. Because like, isn't it only one bond can, I guess, stabilize it?
Let's draw those out.
So you go like all the way around the whole ring.
Yep. If you can do the arrow pushing and it doesn't break any rules, then it's going to do the arrow pushing. And finally, you end up with so there's ultimately 4 resonance structures for a benzylic stabilized radical. Really, really stable. Yeah.
Can you do 10?
Okay. So, for this one, we've got an alkyl halide stirring in some methanol. And so can we do SN2? So we've got to think about SN1 pathway. So if we do an SN1 pathway, our bromine will leave. And so what we're left with is basically this carbocation right here, right? So what nucleophile do we have that can trap that? The OH. We do have methanol in solution, but you can see that I'm not showing any products from the methanol, right? So the only thing that could be doing the addition here would be from the the intramolecular OH group. And so if we do that, I think it's best if you count your carbons here. And so what we're going to end up with is 1, 2, 3, 4, 5, 6. So we should end up with a 6-membered ring. And so we would end up with, let's see, we've got 1, 2, 3, 4, 5, 6. And so a methyl group is 7 off of 6, but because it's an SN1 reaction, we're going to form a new chiral center at that alpha carbon, so we end up with this plus the enantiomer. This one was a tough one, but people for the most part got quite a bit of partial on it. So
That's the question I don't get though.
mm-hmm.
The answer's only, like if you count the carbons, maybe I'm just being really dumb, but if you count the carbons in those two, there's only 6 carbons.
Well, so there's only 6 carbons in both, right? So there's 6 carbons here, there's 6 carbons here, there's 6 carbons here.
Or no,
The oxygen.
Right, there's 6 carbons, but isn't that that's not enough carbon, is it?
So we've got here,
Like there's 6,
Count it O as a
yeah, so it's a 6-membered ring where the oxygen is in the ring,
Oh.
right? And so we've got 1, 2, 3, 4, 5, 6 total carbons in all of these structures.
okay.
Yep. Admittedly, this one was difficult.
Yeah. I guess what's the rationale behind like forming a ring instead of having an OH? I guess what's the reason?
So it's actually a really favored reaction. In fact, it wouldn't surprise me is if we did this reaction in methanol, I still don't think we would see the methanol add into the carbocation. And so the reason for that is to do an intermolecular reaction. Not only do we have an enthalpic factor, right, just the nature of the heat of the reaction, we also have a level of entropy that has to occur, right? We have to happen to have a molecule, our methanol bang into our carbocation correctly. However, our OH group, which is tethered to our carbocation, is always going to be close by, right? And so it removes that entropic, it removes that element of luck, you can say, from the reaction. So it's actually going to be much more likely to do the intramolecular reaction. And we know the 6-membered rings are already very stable with very little strain, and so there's not a lot of reasons for it not to happen. Is it about this? No?
Yeah.
It is. I'll come back to you.
Would this also trigger these SN2 reactions?
What's that?
Would this also happen if there's an SN2 reaction?
So let's see. If it were an SN2 reaction, we'd have to have a base, so we'd have to make the oxygens into a good nucleophile, right? So we'd have to protonate it, and yeah, probably still you'd get the intramolecular. The only difference is that you would only get one of these products because you wouldn't have the received mixture. Yeah, you would get whichever one of these is the inversion product, which just looking at it there isn't obvious to me. Yeah.
Yeah, so would like the first 2 options, would those still be possible though, if they're not like favored, but could those still occur?
So the problem, and in hindsight, I wish I had done this. If I had made this into an O-methyl, that would have been perfectly fine. But to be able to form the products that are shown, we'd have to have water in the reaction, and we didn't have water in the reaction. So, in hindsight, I kind of wish that I had made water the solvent, because in that case, both these 2 and these 2 would be correct. A lot of people put these, the top 2 left, and, I regret not. I regret writing it the way I did,
So
basically.
the only 2 right answers are the 2 bottom, those guys.
The bottom right 2, so. What I was ultimately going for in this reaction was just to have people recognize the intramolecular reaction, but I ended up, right before I printed the exams, I put the methanol to encourage people to do an SN1 reaction, so you get both stereoisomers, and in the process, I just get more confused. I tried to help, and it ended up ruining things. Yeah.
Could you do number 12?
So number 12, for one thing, I gave you some clues. So I gave you the formula, and I gave you how many proton signals we would expect. And so basically, we've got an alkyl halide, but in this case, we no longer just have one alkyl halide, right? We actually have 2 carbon leaving group bonds. And so what that means is that you can imagine, basically, you can do this once, like this, and then you can do it a second time, like this. And so the easiest way to see this, I think, is just to count, again, the carbons. So 1, 2, 3, 4. These atoms that I've numbered here are, we're not separating any of those, so those will stay together. And so then over here, we've got carbon 5 and carbon 6, which stay together. And so you can see we're connecting a bond between 1 and 5, and we're connecting with a bond between 4 and 6. And so what you end up with,
But aren't those not carbons where the oxygen is?
what's that?
Those aren't, like there's not a carbon there, right? Where the sodium oxide is?
No.
It's just a part of the ring.
Are you talking about the oxygen?
Like what you labeled 1 and 4, that's not a carbon, that's just the oxygen.
Correct, yeah, they don't have to be carbons to number them.
Okay,
I'm just numbering to keep track of atoms here.
okay.
And so here we would have 1, 2, 3, 4, and then I guess we connected 4 and 6, and then we've connected 1 and 5. So we end up with that molecule right there. So we would only expect 1 proton signal. Yeah.
Could you do the one below that too?
Yes. All right. So we've got an alcohol, and so we're treating it with tosyl chloride and a base. And so what happens?
You get OTS.
Yeah. So we tosylate our alcohol. So what we end up with is just OTS. And why do we turn an alcohol into OTS?
So we'll get leaving group.
Yeah, it makes it into a good leaving group. So then we can treat that with sodium cyanide. Is cyanide a good nucleophile?
Yes.
It is, and so we're going to do an SN2 reaction, basically. So remember, cyanide reacts at the carbon, and so we'll do an SN2 reaction here, leading us to just one product. That one right there.
Now, with the first step, with the CSCL, why isn't there like a backside attack?
Say that again?
Why isn't there like a backside attack in the first
Because
step?
we're not actually reacting at the carbon, right? We're reacting with the oxygen. So all we're doing is we're changing the OH into an OTS, but that oxygen, that initial, this carbon-oxygen bond that's on a wedge, we're not doing anything to that carbon-oxygen bond. You can see that it's right there in the second structure as well.
So does the H just turn into
The H gets replaced by the tosyl.
Oh, okay.
Yeah.
That makes sense. Thank you.
Yep.
Did the last one of the problem?
All right, so we're spinning this, or I keep saying spinning. We're stirring this in water, and so what kind of reaction is going to happen? Yeah, it's going to be SN1, right? We don't have a good nucleophile, so we want to go SN1, and so if we go SN1, that's going to leave. Can that happen in a primary? It can in this case because it's a allylic, right? So we've got a resonance stabilized cation, so we end up with this structure, which is resonance stabilized to give this structure. I'm sorry, it's the same structure. This structure. So which is the major contributor? Yeah, so here we've got our major contributor, here we've got our minor contributor. And so the more important resonance structure is going to lead to the major product. And so what we'll end up seeing is this plus, yeah, so there's one chiral center. So that OH can be on a wedge or it can be on a dash, so it would be that plus an M2.
Could you do the one above it as well?
Yes. All right, so this one, so if we're treating something with HBr, peroxides, and light, and we're ending up with bromine on the molecule, what functional group must we have in the starting material? Let's remind ourselves back up here. So we treated this with HBr, And so we had an alkene here, right? And so we have to have an alkene, and more importantly, when we do this reaction, is it Markovnikov or anti-Markovnikov?
Anti.
Yeah, so it's anti-Markovnikov. So what we've got to do is we have to draw the double bond, or the alkene that would lead to an anti-Markovnikov product. And so in this case, we've got two possibilities. Are we going to want to draw the double bonds basically here on the left or here on the right?
On the left. Just gonna go in the middle.
So what we're going to want to make sure we do is the one on the right, because the anti-Markovnikov addition to that, the options would be tertiary versus secondary. And so obviously secondary, the bromine on the secondary would be the anti-Markovnikov addition. If we put it on the left side, then the anti-Markovnikov product would have the bromine on the primary, the left substituted. And so basically there were two possibilities. You could either put it on the right or the left, but only the right would lead to our product that we formed. Yeah.
Oh, I have a different question, so.
Other questions about that? Yeah.
We got an
8?
Yeah.
All right, so we've got NBS and we've got light. And so what does that scream if we're using NBS?
It's a radical.
It's a radical, and so more specifically, what kind of reaction? So we use NBS to avoid the electrophilic addition of Br2, right, to an alkene. And so what it is, it's going to be an allylic halogenation. So we've got two allylic positions. We can imagine abstracting hydrogens from either of those allylic positions. So let's see. We would end up with this radical, which is resonance stabilized. To give this radical, and so specifically the allylic halogenations are where I said not to worry about major or minor products, and so that's why I just asked for what would be possible products to form from an allylic halogenation. So we'll also be able to form, let's see, this radical, and so that's it. Those are the really, I guess, the well, so let's go ahead and draw the resonance structure for this. So this is also going to be resonance stabilized. Wait a minute, what did I do? That's not a dash, sorry. We're not doing any chemistry there, that stays a wedge. And so we've also got this. So really there's 4 possibilities in terms of reactivity. So there's 4 carbons that can have resonance type reactivity. So if the product resulting from, we'll say that this is A, B, C, and D. And so these 2 would result from A. This one would result from B. These are from C, and that one's from D. So basically there's a bunch of different radicals, or at least there's 2 radicals that could form. Both of those are going to be resonance stabilized, and so anything, basically any intermediate or any resonance structure we can show as a radical will have radical reactivity, so any products from this will form. So we didn't have to worry about choosing the major or minor in this case. Yeah.
The next one.
All right, so how I regret putting HBr for this reaction. I wish I'd done anything except bromine. The test was littered with bromine radical reactions, and so then I chose that. Okay, so we've got an alcohol, we've got a strong acid. What's the first step? Yeah, I mean, it's going to be acid-base chemistry, and so with our strong acid, we protonate our alcohol. All right, so that will lead to this. And so what's the point of protonating an alcohol?
So they can leave.
Yeah, that turns it into a good leaving group, so we're going to be doing an SN1 type reaction. I mean, just an SN1 reaction, I guess is the way you should say that. And so we've got that. Now we've got to figure out how to get from this to this. And so how do we go from that secondary carbocation to something that will lead to that?
Do a shift.
What kind of shift?
A hydride shift.
Yeah, so we're going to undergo a 1,2 hydride shift. And so that leads to this tertiary carbocation. And so from there, we've got a bromine that was left over. So it can add right back in to lead us to the product. So basically, you protonate your alcohol, you make it a good leaving group, you get a cation, you do a shift, and you're right to your product. Yep.
Number 11, the second one.
Yeah, and so when we talked about, we went as far as saying that basicity and nucleophilicity are relatively similar, especially when we're going across a row. And so what it is we've basically got fluorine, oxygen, and nitrogen all with a negative charge. And so which is the most basic of those compounds? Well, which is the least happy with that negative charge?
No.
Now, fluorine's the most happy, right? And so what it is we go right to left, we look at our nitrogen, and so our nitrogen with a negative charge there is fairly unstable because it's not a very, it's relative to fluorine or oxygen, it's not particularly electronegative. And so we can see that in the pKa trend. So we know that HF has a pKa of I can never remember that, maybe 2 or so, 2 or 3. And then methanol has a pKa of around 17. And then dimethylamine would have a pKa of around 36. It's sort of like ammonia. So we see a pretty big trend in stabilities between those anions. And so since the nitrogen is the least stable, it should be the most reactive and the most nucleophilic. And so we would think that it would be the fastest to react in an SN2 reaction.
We do the first part too.
Yeah, the first part, a lot of people put A. Why can't it be A?
Because you can't extract it.
Yeah, that's an sp2 carbon, and so you can't do the chemistry at an sp2 carbon. So it's really between B and C, and so we can see we're doing it in methanol. And so is methanol going to be an SN2 or an SN1? Yeah, we should be thinking SN1 because we don't have a good nucleophile, so we're thinking about most stable carbocation, and so it's going to be between the secondary carbocation or this resonance stabilized secondary carbocation. So which one's more stable? Yeah, obviously the resonance stabilized carbocation will be more stable, so we end up with B. We may as well do the last one. So the last one has a primary alkyl halide with Na3, sodium azide, and so is azide a good nucleophile? It is, and so we have a good nucleophile, so what kind of reaction would we do?
SN2.
Yep, so we do SN2, and so which of these will be fastest in an SN2 reaction? Yeah, we're looking for the least crowded. So our least crowded is definitely going to be A in that case. So. Yeah.
Does weight play a role in how fast the reaction reacts? Because with the two members, won't that be a lot heavier than the oxygen? Does weight kind of play a factor into how fast the reaction is?
Are you talking about for like the middle one?
Yeah.
No, not really. Ultimately, at the molecular level, things like charge and electronegativity are going to be much more important. It could have a slight impact, but nothing that's going to change, the fact that this is 20 orders of magnitude more acidic. So, yeah.
Also, the second part of that, when you're looking at the pKa, that determines which one's the strongest base.
Uh-huh.
And
Yeah, so the stuff we're doing now, we draw that line at the pKa of 11. And so between these three, knowing what we know now about elimination, let's say that we've got, let's come up with a hypothetical. So let's say we've got this alkyl halide, and so we're going to treat it with three different things. So we're going to treat it with F-, and then we're going to treat it with methoxide, and then we're going to treat it with our N- here. Okay, and so if we treat it with the N-, are we going to do SN2 or E2? Think back to our flow chart. What's the first question we ask for a secondary alkyl halide?
Is it a strong base?
Is it a strong base? And so is this a strong base?
Yeah.
Yeah, absolutely. I mean, it's conjugate as a pKa in the 30s, and so we would expect E2 or SN2?
E2.
E2. And so then we look at methoxide. Is methoxide a strong base? It is, and so again we would do E2. But what about fluoride? Yeah, so fluoride, its conjugate has a pKa of 2, which is less than that magic 11 number that we say. And so since it's not a good, or it's not a strong base, we then ask, is it a good nucleophile? And so certainly a negatively charged halogen is going to be a good nucleophile. And so in that case, we'd actually do SN2.
So SN2 will work with a good, like, if it's the conjugate of a strong a good acid, it will be SN2.
If it is the conjugate of a strong acid, certainly, right? Because anything like HCl or HBr, those are never going to do E2 because those are pathetically weak bases, like bromine and fluorine. Any of the halogens are very weak bases. So, yeah.
So one general question that I want to clarify is, how do you tell strong versus weak nucleophile?
So we made a little list back when we were talking about it. Let's see, it would have been. Let me go a little further back.
It was on the 15th.
15th?
Yeah.
It's further back than I thought. All the way back to tax, man. Okay, so, where is it? Did we pass it? Oh, the nucleophile. Yeah, and so what it is we made a little list of things that are strong nucleophiles versus weak nucleophiles. What we really said is, it's maybe even easier to remember the weak nucleophiles. All we really talked about was neutral oxygen, so water and alcohol. Those just aren't good nucleophiles, and you'll never see N2. All this other stuff that we talked about, so halogens are good nucleophiles. Negative charges on carbon or oxygen or nitrogen are typically good nucleophiles. And then even a neutral sulfur or a neutral nitrogen is a good nucleophile and can encourage SN2. So any of this stuff can encourage SN2. We just have to consider, is it a secondary alkyl halide? If it is, we've got to make sure this stuff isn't too basic to actually prefer E2.
Okay, so yeah, for OH, but if you have N-methyl OH, isn't that weak nucleophile?
Well, sure, but in that case, with methanol, MEOH, the oxygen doesn't have a charge because it's a neutral oxygen. It's bound to two things.
Okay, so all of the charged stuff has to be isolated from the compound, like, because we're often given solvent, right? Which is neutral compound.
Right.
So how do we tell from that neutral compound that they're going to separate into?
Yeah, so what you'll sometimes, the way this is typically done is, let me get off of the notes. So if you're gonna, if you're just gonna stir it in methanol to encourage an SN1 reaction, you'll often just see, we're just gonna say it's methanol. And so that's obviously gonna go SN1. To do the same thing except in SN2, typically you'll still use methanol, but you'll also now have some sodium methoxide in there, right? And so you've got to have some of this. We must have this present the sodium methoxide present to ever do an SN2. If we just had methanol, we just don't have any negatively charged oxygen in there. Yeah, and so it's okay, you know, it's okay to have this mixture of sodium methoxide with methanol. Certainly they're going to be transferring protons to each other, but that's just going to create the same thing, right? It's just going to create sodium methoxide and methanol in a reaction. So it ultimately doesn't matter. And the reason that this promotes SN2 over SN1 is just because it's a lot easier to do SN2 than to form a carbocation. So.
With what we know about elimination reactions, would A on part 2 just go through E2, or would it also?
A on part. Which one? This one?
Yeah.
So knowing what we know now, I don't think it'd make a difference. So I think, you know, that A is going to encourage E2 fastest, just like it would encourage SN2 fastest if it could do, right? So I never really explicitly said SN2 there.
So would we have to, like, if we were given A and then the compound with the bromine, would we have to decide if it was SN2 or E2?
Yeah, that would be perfectly fair. So again, we've got a secondary alkyl halide. So the question we ask first in our flow chart is do we have a strong base? And so this is a strong base, and so we would expect E2.
Okay, so we would think about SN2 for that.
No, and that's why I tried to do the flow chart in a way where you just, you know, you ask yourself a question, and if the answer is yes, you're done. So. Yeah.
So like, I guess like before we did all this stuff, we were just looking at this question like on the exam. We just said that because it was the most basic and it could be the best electrophile out of all of them. Like,
Nucleophile, you mean?
yeah.
Yeah.
Okay.
Yep.
Do you recommend that we memorize just a bunch of PKs?
No. You should just, you know, for the most part, we tend to use the same nucleophiles over and over again, right? We use alkoxides, so O minuses from alcohols. For the most part, we use the same nucleophiles over and over again. So I'm not going to be trying to trick you with things like that. You know, for the most part, we'll use alkoxides like O minuses or maybe an N minus, and you know, it's they generally have the same pKa's. So, and you'll have a pKa table for the exam. So, yeah.
So if you have a situation where you're trying to determine like SN2 or E2, and you realize that like SN2 is favored over E2, does that mean that your SN2 products are like the products, or are they just the major product?
In Chem 206, it is the product.
So you would never be. So if SN2 is favored in a reaction, SN2 products are the products. It's not SN2 or major, E2 or minor.
Right, correct.
And vice versa. Does that apply? Like if E2 is favored over SN2, you're not going to form some E2, some SN2. It's just kind of.
Yeah, no, totally. I think, especially in my class, yeah, you're going to get one product or you're going to get the other product. You're never going to have a mixture. Now, in the real world, you always get mixtures of things when you do. That's what makes chemistry difficult in the lab, is you always have side reactions that give you things you don't want. A lot of what we do is spend our time trying to prevent those other reactions from occurring.
Could you give me 13?
13. Okay, so let's blow it up a little bit. All right, so I thought this was a fairly straightforward benzene splitting pattern, and so I think people for the most part got it. So let's see, we've got 2 doublets and 2 triplets. What's the only thing that will give us that? Yeah, so we clearly got a di-substituted benzene because we've got 4 total benzene protons down in the 7 to 8 region. So remember, we've got, I guess, let's see, we've got 3 possibilities. We could have that, or we could have that. Or we could have that. And so if we've got 4 signals, it's clearly not going to be this one, right? Because in that case we only have 2 kinds of protons. And so that pretty much makes it either ortho or meta. And so which one, you can, or really you can just see, you look up here and you see that one of these should be a singlet, and so we don't have any singlets. And so what that tells us is that we've almost certainly got an ortho splitting pattern of some kind. So that's it, that's fragment number 1. And so the IHD for this one was 5, so that also leads to to a benzene fragment being very possible. So we've definitely got this. And so then what else do we have?
We have the pattern that shows like CH2, CH2, CH2.
Yeah, so clearly we're going to have CH2, CH2, CH3, right? And so that corresponds to that, and that pretty well. So that makes sense. Our CH2 is downfilled, or at least this one right here is downfilled around 3. What would put it around 3? Yeah, but not directly connected to an oxygen, right? So if it's directly connected to an oxygen, we typically see it around 4, or maybe slightly further downfilled than 4. So you're right, it should be next to something electronegative, but not directly next to something electronegative, probably. Let's look at our IR pattern. So what do we see clearly going on in our IR spectrum? We've definitely got a carbonyl, and we've definitely got an OH. Switch back to red. So carbonyl. So over here, we've clearly got an OH. And so there's 2 possibilities for this CH2 to be next to an oxygen. Which do you think it's going to be next to, the alcohol or the carbonyl? I'm sorry, go ahead. I mean, could it be next to the alcohol?
No.
It couldn't, right? Because that would be it for the molecule. And so it's almost got to be next to the carbonyl. And so we end up with a fragment that looks like that.
Wait, why does that have to be next to the carbonyl?
Because if it were next to the alcohol, we'd have 2 terminal ends, right? And that would be it. The molecule, we couldn't add anything to it. All right, so we've got the carbonyl there that shifts the CH2 downfield. And so that pretty much leaves this singlet around 4.5 left over. And so it's probably a CH2 of some kind, but what is it almost certainly next to? The OH now. And so that makes sense because if it's directly next to the alcohol, it's going to be a lot further downfilled. And so in this case, it's even more downfilled because we'll see that it's connected to the benzene. So we've used all of our atoms up. Our 3 fragments are CH2, OH, and then carbonyl, CH2, CH2, CH3, like that. So we just put those together the only way that they can go together. And so we end up with that molecule. A lot of people did things like put the carboxylic acid, or at least a kind of carboxylic acid. From looking up here, how do you know it? What's the strong evidence that it's not a carboxylic acid?
That you don't have the shifts at 11.
Yeah, and so on your chart, you were told that a carboxylic acid shift, you'd expect a proton down around 10 or 11, and you can see here, you've got the likely OH peak at 5, which more likely corresponds to an alcohol than a carboxylic acid. So this right here says OH, not carboxylic acid.
How do you know that your CH2, that like lonely one all by itself, isn't connected to the, how do you know that that doesn't go in between the ring and the carbonyl?
Let's see.
Yeah, that trips me up.
Yeah, because I put like the alcohol by itself and then the CH2 in between.
So, yeah, so you're saying why can't we have something that looks like that?
Yes.
So again, I just don't think, so let's think about what we've what we've got here. So that's indicating that this CH2 is this peak right here. But again, it's just so far downfield. It's over 4.5 ppm downfield that it's almost got to be directly connected to a heteroatom. So I think that's probably the strongest piece of evidence that doesn't work. The graders and I went over this and we tried to see if anything would really work other than the answer, and we felt pretty confident that there were pieces of evidence that would go against.
So if that were the answer, the one in red, your CH2 would be like closer to like 3.5 or 4.
Yeah, so I would expect it to basically be maybe 3 to 3.5 ppm.
Okay.
Yeah, it's going to be a little. Anytime you have it next to the benzene will shift it down a little bit, but I wouldn't expect it to shift it all the way to 4.
Okay. And it's
Yeah.
not shifted by the oxygen?
It is
But
by
still
the
not-
carbonyl, you mean?
Yeah.
It is shifted by the carbonyl, but a carbonyl shift is usually 2 to 2.5.
Okay.
And so this carbonyl ends up being a little further downfield, I think, just because they're both connected to a benzene ring. So, yeah. Yep.
Sorry, I might have just missed you explaining this, but for the final product, why did you put a CH2 between the...
That's not the final product. We were just looking at another possibility.
Oh, to see if that works rather than
Yeah,
having
the-
the CH2 with the OH.
Right, so that's
yes,
the-
there we go. Okay,
yeah.
that makes more sense.
Yep.
Can we use through some of the problems like that you posted as practice?
Yeah. I've actually been a little surprised that we haven't done any of that. So this would be This would be more chapter 9, wouldn't it?
Yeah.
Okay.
Can we do 9.37 C, E, and F? Or just, you know,
We'll see. We'll see if we can do all this. 937,
yeah.
C, E, and F.
Yeah.
And so it says, draw structural formulas for the alkene formed by treatment of each haloalkene or haloalkane or cycloalkane with sodium methoxide. Assume C2 mechanism. So I think we can probably do that pretty quickly.
He posted this yesterday.
Okay, but like,
9. Okay, so we're looking at 9.37. So which letters again?
C, E, and F.
C. So C. We have that. And so we're treating with sodium ethoxide, which is a strong base, and so will promote E2 reaction. And so what we've got to do is, and so what does it say? It says draw structural formulas. So I guess it wants major products. They're never very clear.
That was another question I had that's just general. If you have an E2 reaction and you ask for the product, obviously that a lot of them are going to have resonance forms. Should we just draw the most stable resonance forms?
I'll try to make it clear in an exam question. It's just another reason that I hate this book is that the problems are not always very clear.
Okay. But so on the exam you'd say either like just draw the most stable, which would be the most
Yeah.
substituted.
I think it'll be pretty straightforward.
Okay.
All right, so we've got to do chair analysis. We've got to see, where we can do this. So, what we've got is, let's see, we can number 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. And so we've got a methyl up, and then our chlorine down. And so really what we can say is that we've just got to, we're never going to do E2 unless our leaving group is axial, right? Because that's the only way we can have anti-periplanar, or what I didn't say anti-coplanar. They use periplanar at Michigan, so I've had to change my wording. So anti-coplanar, we've got one of them there, right? And that's pretty much it. That's the only beta elimination we can do, and so when we react with our sodium ethoxide, we'll form a new double bond between 3 and 4. And so the only product we can end up with will be this product right here. And so this isn't the Zaitsev product, right? This is di-substituted alkene, whereas the double bond between 2 and 3 would have led to a tri-substituted alkene, but in this case we can't form the Zaitsev product just mechanistically, and so we share this product as the only. All right, so the next one is D, or
E.
E. All right, so E looks like this. And so now we don't have to worry about the chair analysis because our leaving group is no longer on the chair, it's on the CH2
So you won't
connected
have to
the
do
chair.
that chair analysis if it's.
Right, because the beta protons, let's see, well, actually we do.
But you
No.
still have to worry about whether or not they're.
Yeah, because the beta protons in this case are actually going to be on the ring. So let's go ahead and do a chair analysis. Let's say 1, 2, 3, 4, 5, 6. Let's see. I'm actually not sure how this is going to work out. Let's take a look. All right, so we've got 1, 2, 3, 4, 5, 6, and so our chlorine, it's not a chiral center, so we can pick either. We'll just go ahead and draw it like this. This is a tough one. Alright, so we've got kind of something that looks like that. And so if we do a bond rotation, seems like we can get this to have an anti-coplanar beta hydrogen. As soon as I start to like some problems in this book, I go back to hating them. I just feel like they make them too difficult. Or not maybe too difficult, but just not testing the basics very well. So I think, we could have we could end up with an anti-paired planar proton there. So I think we would end up doing elimination here. So we've got our base. And that's the only, it's the only
Wait,
beta.
but your chair didn't actually flip.
We didn't need to flip the chair. We're just doing a bond rotation because
Oh.
yeah, it doesn't matter. There's only one beta hydride, regardless here. So that means we're going to form basically this exocyclic alkene right there. That's the major product. Haley?
Can we do an example of where you do have to flip the chair in order for it to work, and how that makes
So-
the final product look different?
Yeah, so that's kind of like this one up here. So if we look at the other chair, we've got 1, 2, 3, 4, 5, 6. And so 2. Oh wait, I drew the same chair. Oops. Hold on, we can just renumber. Or we'll just draw it. Okay, so that means this is 3, 2, 1, 4, 5, 6. And so our methyl on 2 is now equatorial. Hydrogen is straight down. On 3, we've got this hydrogen straight up. Chlorine equatorial. And so then on 4, we've got this and this. And so what it is to figure out what products we can form, we've got to draw out the chairs. Because just looking at this, we do have multiple beta hydrogens, right? We've got a beta hydrogen there and a beta hydrogen there. And so you could think, well, why, certainly we could do the beta elimination to either of the beta hydrogens, but when we do the chair analysis, well, we're not going to be able to do an E2 reaction when the leaving group, the chlorine is equatorial, as it is here, so we have to draw the other chair where it's axial. And so when it's axial, we can see that with the stereochemistry given, this beta proton on carbon number 2 is just not anti-coplanar, right? And so we can never eliminate to get that double bond between 2 and 3. We're only going to be able to form the double bond between 3 and 4.
So you you just do the chair analysis to figure out which beta proton you use.
Yeah, basically you want to see, you can see how many beta hydrogens you have in this picture, but to see which beta hydrogens can actually undergo an E2 reaction, we have to draw the chair.
Is there ever more than one?
Yeah, so, for example, let's say that we flipped the methyl stereocenter such that now it were equatorial, and so then this hydrogen would be axial. In that case, we would then be able to form both products because this proton would be up.
You can't just do that because that's not what they gave you, right?
Right, yeah. No, in this case, you can't do it because that'd be a different molecule.
Yeah.
But so the stereochemistry, basically what we end up seeing is the stereochemistry matters a lot in determining which product we can get. And then F, what was it?
Yeah.
So for F, we've got this right here. And so we have a beta hydrogen at this position, and then we've also, I guess, got a beta hydrogen at this position. So we can eliminate either perfectly fine. Which is going to be favored?
The one going down.
Yeah, so let's see what happens. If we eliminate this one, we'll end up with this product. So if we eliminate the top one, we'll end up with this product. And so here, this is, the bottom one is di-substituted. The top one is tri-substituted. So which one is the Zaitsev product?
Top one.
Yeah, so here's our Zaitsev. And so that makes the top one our major. Yeah. Yeah.
So we talked about like SN2 and SN1 with the different like the polarity product solvents and everything, and I was wondering if like the same rules basically apply to solvents for E2 being one.
Yeah, I mean anything that's going to stabilize a cation we would think lead to more E1 reactivity. So it stands to reason that we would see something.
Do 1,2 shifts ever occur in SN2 or E2?
No, because you have to have a carbocation.
Oh, duh. Okay.
I'm gonna make this department buy me a new one. You've been driving me nuts for a month.
So, like, those structures you drew, are there resonance forms of them? Like, for the tricep, like, for that top product, is there a resonance form?
I mean, anytime you've got an alkene, you can draw a resonance
Right,
form.
that was the bad way to ask the question.
And in fact, I would even say that this top one is more stable, not because it's tri-substituted, but because it's next to this pi bond, and so you can have lots of different resonance structures where these p orbitals are interacting with these p orbitals, but that's more like an organ.
Right, so like I said, when you ask us to draw these products, we just draw one, the most stable resonance form.
Yeah, because if I ask you to draw a product, you could draw, I mean, technically, unless I said draw the most stable resonance form, you could draw any resonance form, and that's an accurate picture of all of them. So, because things that undergo resonance, you can't actually draw one true picture of all.
Okay.
Yeah.
And what if some of the, I feel like some of the questions in the textbook didn't give us the stereochemistry of the reactants.
Like, you have an example?
No, because I just wrote in my question, what is stereochemistry isn't given. But will you give it to us if we need it?
Yeah.
Because like we can't do, I guess like we can't do a chair analysis if we don't have the stereochemistry.
Yeah, and so for example, like in 9.47,
Yeah, that was.
yeah, but none of, see what it is, and I see what you're saying, but none of the places where it's lacking stereochemistry are actually stereocenters.
Okay.
So it doesn't matter.
Okay. And then this is really, can we have like, can we do like
Yeah.
one.
Which one?
59.43 BFs.
How about one of them?
They're like, it's just like, does it match SN2?
Oh. Alright, so consider the following statements in reference to SN1 and all the things we put. To which mechanisms, if any, does each statement which letters?
B, F, and G.
B,
Yeah, mostly like didn't know what it meant when it said like a zero order base. Like, what's that?
B, F, and G. And so if something is first order, basically it means that it is in the rate law. If it's zero order, then it means the concentration doesn't affect the rate of the reaction. So for B, it says is first order in haloalkane and first order in nucleophile. And so that's something
So
where
that's
the
SN2
yeah SN2.
and E2.
It says nucleophile, so I guess we just go with
okay.
SN2. F is first order in haloalkane and zero order in base.
So that would be SN1.
Well, it's base.
Oh, so it'd be E1?
E1. And then G is first order in haloalkane and first order in base. So that would be E2.
SN, okay.
Yep.
Cool.
Yep.
Thank you. Sorry, I had to like.
It's okay. I just want